Hi everyone, we are from Group 5. Our group will be presenting our task on digital signal processing (DSP), focusing on FIR and IIR filter design for audio noise removal. The overall workflow begins by sampling the audio signal, following by analyzing its frequency components using the discrete Fourier transform. Based on the spectrum, we design suitable filters, analyze their characteristics, apply them to the noisy signal, and finally compare the filtered results in both the time and frequency domains.
Alright, let's start the process by sampling the original audio signal. The audio signal is initially a continuous time signal, which cannot be processed directly by the MATLAB. Therefore, we use sampling to convert it into a discrete time signal, represented as Xn. As shown in the graph, the continuous signal is converted into a sequence of digital samples for further processing. Next, we analyze the frequency content of the signal using the discrete time Fourier transform, DTFT. Since DTFT cannot be computed directly in the MATLAB, that's why we use the fast Fourier transform FFT to obtain a discrete approximation of the DTFT spectrum. From this FFT spectrum, we can see that the useful signal components are mainly concentrated around 440 Hz and 880 Hz, while unwanted noise exists outside this range. Therefore, a bandpass filter will be used in the next stage to preserve the useful frequency and reduce the noise.
Next, I'll explain the FIR filter section of our design. Based on the previous step, we found that the useful audio components are mainly between 300 and 1200 Hz. Therefore, to preserve this range and eliminate noises, we choose a passband FIR filter. In MATLAB, these cutoff frequencies are first normalized by dividing by the Nyquist frequencies. Next, we design the filter using the windowing method with Hamming window, which is described by this equation. The Hamming window converts the ideal infinite response into a practical finite impulse response by tapering the edges gradually instead of abruptly truncating the filter, which can help to reduce ripple in the passbands. To verify our design, we look at the frequency response plots. It shows that the frequency between 300 and 1200 Hz are passed, while the noise outside the range is greatly attenuated. And the straight line in the phase response indicate that the filter has a linear phase, meaning the waveform shape is preserved. And finally, the impulse response plot confirms that the filter has a finite and symmetric response, proving that our FIR filter is stable and ready to be used in the convolution step.
Okay, now I explain the IIR filter design. First, we design a 6-order butterworth bandpass filter using the MATLAB function butter. Next, we use this FREQZ function to plot the frequency response. The top graph is the magnitude response. You can see a relatively flat passband, meaning the desired frequencies are preserved while the response drops sharply outside the cutoff frequencies, effectively attenuating unwanted noise. The bottom graph is the phase response, which shows that different frequencies experience different phase shifts. This non-linear phase response is a typical characteristic of IIR filter. Now let's revise the DSP keyword, which is bilinear transformation here. Bilinear transformation will convert an analog butterworth filter into its digital equivalent by mapping the S-plane onto the Z-plane, allowing it to process discrete time signal. Finally, we use this IMPZ function to obtain the impulse response. The graph shows oscillations that gradually decay towards zero but never become exactly zero because the filter uses feedback, while the decaying oscillations indicate that the filter is stable.
Looking at our Z-plane analysis, the pole-zero plot provides immediate visual confirmation of our system stability. For the FIR bandpass filter, you can see all 79 poles strictly clustered at the origin, proving it is inherently stable. For our IIR filter, every single pole lies safely inside the unit circle, confirming that its ROC includes the unit circle, ensuring absolute stability. Finally, for the convolution and filtering stage, well, filter mathematically represents a linear convolution step between our noisy input and the impulse response. We execute this by MATLAB filter function for structural consistency across both design, effectively clearing out the noise.
Finally, we reach the output stage. In the output stage, we compare the noisy signal with the filtered results in both time domain and frequency domain using FRR and IR filter. From the time domain graph, the filter signal is appeared to be cleaner as it shows less fluctuation than the original audio. This shows that the both FIR and IR bandpass filter has successfully reduces noise components outside the selected frequency range while preserving the main signal between 300 Hz and 1.2 kHz. In the frequency domain graph, we can see that the frequency component within selected passband between 300 Hz and 1.2 kHz are preserved, while the unwanted frequency component outside the passband is attenuated. Now, let's look at the comparison. The FIR filter is always stable and gives a smoother response, but it may need a higher filter order. The IR filter is more efficient and sharper, but stable checking using Z plane is required.
Now let us listen to the original audio signal and audio signal after applying FIR and IR filter.
0125 0125 0125.
In conclusion, both filters can successfully remove the noise through different methods and trade-offs. For the FIR filter, we use the windowing method with a Hamming window, which guarantees absolute stability and a linear phase, but requires a higher filter order. For the IIR filter, we use a Butterworth design via the bilinear transformation, which gives us a much sharper roll-off and higher efficiency with a lower order, but at the cost of non-linear phase. So ultimately, when choosing and designing a filter, we need to decide between prioritizing sound quality or saving processing power. That's all from our group. Thank you.